In this video, we're going to continue our discussion of annuities, but we're going to look at situations where annuity payments are used to pay off an obligation rather than to grow an account. So contrasting the two situations, the one we talked about in the last video and the one we're going to talk about here. The one we looked at in the last video involves what we call the future value of an annuity. So future value means what is our sequence of payments worth in the future. It's the sum of all the payments we make and then all the interest that we accrue on those payments. And what we want to determine is, based on a payment plan, based on how we know our account is going to accrue interest, what is the entire account going to be worth in the future? So you can think of different kinds of questions that might be answered by using a formula like this, specifically the future value formula. So one question that might be answered by a formula like this is, if I make equal periodic payments, what will my account be worth in the future? Keywords: in the future. What is the account worth in the future in order to make these payments and then grow the account based on interest? Or what payments do I need to make now and continue to make over time to meet a goal in the future? If we're asking the first question, then what we're trying to determine is the actual future value. If we're asking the second question, then the idea is that we already know the future value we want to get to. We know what the value is that we want to reach in the future. And the question is, how would we structure a sequence of payments so that we could meet that goal, knowing that we make payments now, we accrue interest on them, and that allows us to meet a goal in the future without needing to deposit all the amount from our own particular funds. Now, what we're going to look at here is what we call present value rather than future value. Present value is actually another word for principal. So the present value of an annuity specifically represents the principal that would have to be in an account now in order to make payments in the future. Now, we're really going to look at it from the standpoint of something like a loan. In other words, if you think of the principal amount of a loan, say you buy a car, something like that. The principal amount of the loan is the actual amount that you're financing. It's the amount you're getting a loan for. Well, as you pay off that loan, you have to consider the fact that you're still accruing interest on the portion of the loan that goes unpaid. So the present value for your annuity payment, your sequence of payments that you're making to pay off this loan, it represents how much you're going to end up having to pay month to month, typically, in order to pay off a certain amount of principal, keeping in mind again that not only you're paying off principal, but you're also paying off the interest that you continue to accrue on whatever that loaned amount is. So what kind of questions might be asked if we're talking about present value? One question would be, what equal periodic payments will I have to make over time to pay off a current obligation? That represents what we're going to think of from the standpoint of a loan. How do we structure a payment plan so that we don't only pay off the principal, but we also pay off all the interest that we know continues to accrue over time? In general, you pay off more than the principal, right? By the time you paid off your car, you paid off the amount you were loaned as well as some additional money. That additional money represents the interest you were charged. Now, another way this might be phrased, it's a less common situation, but I'll try to give you an example. What lump amount do I need now in order to make equal periodic withdrawals in the future? Now, this again assumes that we're putting money into an account that's going to accrue interest. So where might a question like this be asked? Well, suppose your parents want to set you up an account just to pay for basic expenses during college, pay for gas, pay for food, those kinds of things. But rather than making periodic deposits into your account, they want to put a bunch of money in at one time, and that's going to keep you covered for the year, or maybe you're lucky and it'll keep you covered for the 4 years. Essentially, what we have to consider is, number one, we're putting an amount in the account. Number two, that amount is accruing interest. But also number three, you're continuing to make withdrawals from the account. So how much money would you have to put in, or would your parents have to put in on day one in order to allow that amount to accumulate interest, but put enough here now, knowing that it will accumulate interest in the future, but also let there be enough so that you can make periodic withdrawals over the course of the next year or the next 4 years. So say for instance, they want you to be able to withdraw $200 per month to cover gas, something like that. Hopefully you don't need $200 worth for gas, but maybe for eating out, stuff like that. They want you to be able to eat out. Well, they're going to put money in the account knowing that that money will collect interest, but also keeping in mind that while some collects interest, you're also making withdrawals from the account. But the idea is that at the end of the year, at the end of 4 years, whatever, you will have used all the money in the account. Some of the money you use will have come from the money your parents put in the account originally, and some of the money you use will come from all of the interest that was earned on whatever balance the account maintained. So again, that's not going to be as common of a situation. Typically, we're looking at situations where we're paying off a loan, but it's the same kind of idea. This idea that we're starting with money now, this money accrues interest, but the goal is to take that particular balance and then decrease the balance over time to zero, decreasing not only the principal to zero, but also decreasing the interest to zero. So just like with the last video where we looked at an actual mechanical example to show what's happening over time, I want to look at another example where we think more about the structure of what this annuity is looking like and how we can apply this to just the general idea of compound interest. Now we have to think about the distinction between future value and present value. Future value is another word for account balance. So the value for A that we used in our standard interest formula, we can also think of that as being the future value. That's the value that the account has in the future. Now the term present value, that's another term for principal. So when we're looking for the present value of a sequence of payments, we're looking at principal. So if we were going to relate it to our standard compound interest formula, when we're talking about the present value, we're talking about the principal for the account. So here's our example. How much should you deposit in an account paying 6% compounded semi-annually in order to be able to withdraw $100 every 6 months for the next 3 years? And we want to make the distinction that after the last payment is made, we want the account to have decreased to zero. In other words, we've used up all the money, there's nothing left in the account. Okay, so the fact that the balance in this account is decreasing, that is our indication that we're looking at a present value situation. Essentially what we want to know is what do we need to put into the account now in order to cover these planned withdrawals in the future. This is basically like the parents giving you money and then you making withdrawals. How much do they need to put in now in order for you to be able to withdraw $100 every 6 months for the next 3 years? Well, how much money are you going to be taking out in total? If you're withdrawing $100 every 6 months for 3 years, then you're going to withdraw a total of $600. So every 6 months would be twice a year, and then we're covering 3 years. So that's going to be 6 withdrawals of $100. You're going to withdraw a total of $600. But does that mean that they have to put $600 in the account for you? The answer is no, because again, you have to think about what's going on behind the scenes. When they put money in the account, that money accrues interest. Every 6 months, you take out $100, but whatever's left in that account still accrues interest. So they don't actually have to put a full $600 in the account in order for you to be able to withdraw $600 across the next 3 years. They only have to put enough in the account so that interest will do the rest of the work. So what we're looking for is what would the principal have to be in order for you to be able to cover all of these withdrawals in the future. So here's our compound interest formula. If you were to think of solving for principal, since principal here is what we're thinking of as the unknown, A, the account balance, is how much we want to be able to sort of cover with that particular principal. So if we were to isolate our P is multiplied by this value, 1 plus I to the n. So if you were to take that entire value, which represents ultimately one number multiplied by P, take both sides of the equation and divide by that particular factor, this would be the value you have for P. So P would be A divided by 1 plus I to the n power. All that is taking that particular value multiplied by P, divide it and move it over, and then isolate P. Now another way to write this is actually like this. Anytime you have something in the denominator with an exponent, another way to write something involving an exponent in the denominator is to write it with a negative exponent. A negative exponent actually means move it to the denominator. So you can convert either way. In this case, this is just going to be easier for us to write. Now, this is a little bit beyond what we need to be able to do, but I just want to show you this. It's going to simplify some of the things we have to do here. It's going to make the math look a little nicer. Okay, so we're accruing interest across this 3-year period. How are we accruing interest? Well, the account pays 6% interest, and that interest is compounded semi-annually. So 6% across the year, but we're making periodic payments twice a year and we're accruing interest twice a year. So we take our annual rate, divide it by 2. That means the periodic rate is going to be 0.03. You'll notice all of these numbers are the same as what they were in the last video when we looked at this similar example in the last video. But now we're talking about, rather than growing our account to a particular balance, we're talking about covering these payments in the future and then decreasing the account balance to a particular value, in this case 0. So this is an expression representing the principal, the deposit you would need to make today in order to have a particular amount in the future, which we'll call A. Now, just like with the future value situation, we have to consider the effect that interest has on every single payment and every single withdrawal we're making. So in order to meet a payment that we're making now, in order to withdraw money now, more of that money needs to come from our own funds. Why is that? Well, if we're making a withdrawal early on, the money that we're making that withdrawal from hasn't had a lot of time to accrue interest. So if we want to get to $100 within a year, we need to have more money now because there's less time for interest to accrue. However, if we want to make a withdrawal of $100, 3 years from now, the particular money we have in the account to cover that withdrawal has had more time to sit there and to collect interest. So the payments or the withdrawals we're going to make in the future don't need as much principal now to cover them, whereas early payments need more principal to cover them because they have less time to accrue interest. Now, what does that look like from a formula standpoint? That's kind of confusing to wrap your mind around, but we can see what this looks like just looking at the formula and thinking about what A represents and what P represents. Okay, now in this case, A for each of these situations is going to be $100. A is going to be the value that we need to cover. It's the value in the account that we need to cover. Well, we're making $100 withdrawals, so the amount we're withdrawing is going to be $100. Okay? P is what we have to have now in order to make that $100 withdrawal. I and N still mean the same thing. So I still means the rate per period, and N still means the number of interest periods we have in order to get to one particular point in time. So what's happening here is we're depositing money in the account today. Right now we deposit money in the account in order to meet these $100 withdrawal requirements over the next 3 years. Okay, so we don't know how much we're depositing now, but we're making some deposit. The question we're trying to answer is, what do we need to deposit now in order to make all of these withdrawals? We want to withdraw a total of $600, so how much do we need to put in today in order to be able to withdraw $600 based on the fact that our account accrues interest? So we're putting a certain amount in the account, day one, okay? In 6 months, so at the end of June, we plan to withdraw $100, okay? So we need to know how much money had to be in the account on day one in order to cover this $100 withdrawal that we're making here. In other words, what amount of principal needed to be in the account in order for that principal to accrue enough interest in order for us to be able to get $100 out of the account? Well, what we have to think of is how long that particular amount has had to accrue interest. If we put the money in the account right now, January 1st, or the end of the previous year, if you want to think about it that way, how much time has elapsed before we have to make a withdrawal? Well, 6 months has elapsed before we make a withdrawal. In other words, 1 compounding period. So whatever we put in the account now has accrued interest over 1 compounding period. So in order to cover our first withdrawal of $100, the amount we need to cover that has had 1 period over which to accrue interest. So to cover this single $100 payment, we need enough money so that 1 interest period will take the original investment and will grow it to enough to be able to withdraw $100. So in this case, N is going to be 1 because the particular amount we have in the account has had 1 interest period in order to grow. So $100 is the amount we want to have. It's the amount we want to have in the account so that we can withdraw it. We know our periodic rate is 0.03, so 1 plus 0.03, there we go. And then it's to the negative n power, because remember we solved for principal. So A is $100, I is 0.03, and then in this case, negative n is going to be -1. Again, because n here is 1 period. We had 1 interest period to grow the account to enough that we could withdraw this $100. Now we withdrew $100, but there's still money in the account. There's money that potentially came from interest, and there's also money that came from that original deposit. Now at the end of December, we also want to withdraw another $100. How long has the money had to sit there and collect interest so that we can make this withdrawal? Well, here's where we deposited it. It sat there for 1 period. Now it's sat there for 2 periods. So at this point, when we make this $100 withdrawal, our money has sat in the account for a total of 2 periods. So in order to make this $100 withdrawal, in order to have this $100 in the account, that's going to be our value for A. The principal we need to cover this, the amount we need deposited on day 1 to cover this payment, has had 2 periods to accrue interest. So the value is going to be 100 times 1.03, so 1 plus our periodic rate, but now it's raised to the -2 power because we've had 2 interest periods, all the way down to our very last withdrawal. So at the end of the 3rd year, we want to withdraw our last $100. How long has money had to sit in the account in order to grow to $100? Well, 1 period, 2 periods, 3 periods, 4, 5, and then 6. So at that point, to withdraw this last $100, our principal has had 6 periods over which to accrue interest. So the amount of money we need to make this final payment has had time to accrue interest 6 times. So its value is going to be 100 times 1.03 raised to the -6 power. Now, understanding what's going on here is a little bit more difficult than understanding what's going on with future value. So I want to go through and I want to evaluate some of these numbers just to show you what's really happening. Seeing some concrete numbers will hopefully make things a little bit clearer. So I want to evaluate the first, the second, and then the very last value. So 100 times 1.03. And now we're raising it to the -1 power. Now be careful when you type in your exponent. You have to use the negative button, not the subtract button. And again, if your calculator doesn't format the exponents, it just draws the up arrow, make sure you put the -1 in parentheses. Otherwise, your calculator may not evaluate the exponent correctly. So -1 power. And that's going to be $97.09. What this represents is the amount of money we have to have deposited in the account today in order to be able to withdraw $100 6 months from now. So as long as we deposit $97.09 today, then this account will grow that amount to $100 after one interest period, and we can make that $100 withdrawal. Now, do we expect the next value for principal to be higher or to be lower? Well, let's see what we actually get. So 100 times 1.03, but now it's raised to the -2 power. Well, that's going to be $94.26. Why did it go down? Well, again, you have to think about what this represents. This represents the amount we have to have in the account today in order for it to accrue enough interest to be worth this amount in the future. Well, why is it less? It's less because if we deposit a particular amount today, but rather than giving it one period to accrue interest, we give it 2 periods to accrue interest, we don't need as much at the beginning in order to meet our goal in the future. Because we've given it more time to collect interest, we don't need as much at the beginning, because more of that goal, more of that $100 goal is going to come from interest than it did the previous time around. So it makes sense that the balance is going to decrease because we don't need as much on day one in order to cover things that are further out in the future. Now, what about the very last $100 payment or withdrawal we have to make? 100 times 1.03, but now we're raising it to the -6 power. And that's going to be $83.75. And as it turns out, that's going to be the smallest value in this particular sequence. This is how much money I would have to deposit today in order to be able to withdraw $100 from this account 6 periods or 3 years in the future. And again, it's the lowest amount because that last payment, the money we used to cover that payment, has had so much more time to accrue interest than the others. It's going to be the smallest amount. Now notice the highest amount and the lowest amount, they're all less than $100. All of these values are going to be less than $100. So we're withdrawing a total of $600 from the account, but the individual amounts deposited to cover those particular withdrawals are all going to be less than $100. The reason for that, remember, it's interest. So we're depositing money today knowing that our deposit is going to accrue interest, and all of that additional interest we accrue is going to help us cover these payments in the future. So if we were to take all of these values and add them up, these 3 plus the other 3 we didn't calculate, that sum is what we call the present value of this annuity. So the actual annuity payments are $100. We're making these payments, but if we take all of these original values, these individual principal values, and sum them up, that represents all the amount of money we need to have in the account today in order to make these payments in the future, knowing that interest is going to cover some of the situation. So that's one way we can look at a present value problem, and that's sort of the mechanics behind it. Now, as with future value, we don't have to do this by hand every time, and as with future value, suppose you had more payments over a longer period of time. Well, doing this by hand would become very tedious. So the good news is we also have a formula that's going to take care of this situation for us. So same variables, but the formula is structured in a different way. So again, we're going to let PMT be our payment, but now we're thinking of it as paying the money out so that we can decrease the account, so that we can pay off the account, or so that we can use up the money in the account like we just did in the last example and take the balance down to 0. So here's our formula. Again, same variables. I is our rate per period, and N is the total number of periods, representing how many times we accrue interest, and then also how many times we're going to make payments from this account or withdrawals from this account until it decreases to a balance of 0. Now, typing this into the calculator is going to be slightly more complicated, specifically because the subtraction with 1 is rearranged. So I'll show you how to work your way around that. This is going to be one where you're definitely going to want to do it step by step and not try to do it all in one line. It's typically not a good idea here to try to do everything in one line. So let's use this particular formula and let's determine what the present value is going to be for that last example we looked at. So we want to know what's the present value. In other words, what do we need to deposit as a lump sum in order to meet our goal over the next 3 years, and then how much of it is interest. In other words, how much of that obligation for withdrawals is going to be met by our money, and how much of it is going to be met by the interest that we earn from the account. And as we've determined, the present value will be less than that total of $600 that we want to withdraw, because some of that goal is going to be met by interest. Now we know our rate per period, we know there's going to be 6 periods. All we need to do is plug that into our formula. So our payment, our withdrawal, is going to be $100, and then our interest rate per period, 0.03, and the negative n is going to be -6 in this case. So just like before, let's go one operation at a time. So we'll start in the numerator, start inside parentheses. So 1 plus 0.03. Okay, now we're raising that to the -6 power. So raise that to the -6 power. Now again, if you have the up arrow, as opposed to a calculator that actually formats an exponent, make sure you put parentheses around that exponent of -6. Okay, now here's where things get a little bit different. At this point, if we were using the future value problem, we would just take that number and we'd subtract 1, right? Because it was parentheses, exponent, then -1. It's flipped here, so think about the structure. It's actually 1 minus that number, rather than that number minus 1. So we're gonna have to use the ANS button here. So we're gonna start it with 1 minus, but what we wanna subtract is this number that we just found. So I'm gonna pull up that number, I'm gonna copy and paste it by doing second and negative, which again gives me ANS. So there we go. That's gonna be the whole numerator, so 0.16 ... Now we're dividing that by our interest rate. Again, normally when we divide, that's going to decrease the output, but because we're dividing by something that's less than 1, that's actually going to take our numerator and it's going to increase it. So divided by 0.03, and there we go, just as I expected, it's going to increase it, so about 5.42. This number is now multiplied by that payment. So you'll notice with interest, with future value, present value, all of them, all of the actual calculations you do, you always multiply by that payment or principal amount last. That's always going to be the last step. So multiply that by 100, and that's going to be our present value. So $541.72. Now again, what does this represent? This represents how much money I have to put in the account on day 1 in order to be able to cover these $100 withdrawals over the next 3 years. It's less than $600 because the rest of the money we need to cover those withdrawals is going to come from the interest that we earn. So $541.72 worth of our withdrawals comes from our money deposited on day 1. The rest of it comes from the interest that we earn over those 6 compounding periods. So in this case, our interest calculation is kind of flipped. It's going to be the payments that we're covering. It's still the total payments, but now it's going to be payments minus our present value, whereas it was flipped when we were talking about future value. If you're not sure which way it's going to go, in general, one way is going to give you a negative number and one way is going to give you a positive number. A negative number does not make any sense in terms of interest. So if you flip it and subtract in the wrong direction and get a negative number, that's your indication that you rearranged the subtraction. You did it in the wrong order, so you need to go back and you need to do it in the opposite order. So we're making a total of 6 $100 withdrawals. So $600 is the amount we have to cover. And then $541.72 of that was covered by our payments. And so the rest of it, in this case, $58.28, that's what's covered by interest. So once we have our deposits plus our interest that's going to accrue over those 6 periods, that's going to be enough to cover those $100 payments over the next 3 years. But again, like we demonstrated on that table, keep in mind the money we withdraw at the beginning, More of the principal is going to go towards that money than goes towards the last withdrawal. The last withdrawal comes from money that's had more time to collect interest, whereas the first withdrawal, there's only been one period for that to collect interest. So more of that $100 has to come from our money, less of it comes from interest. So that's going to be a slightly less common situation in terms of looking at the use for the present value annuity formula. Typically, we're going to use this from the standpoint of covering a loan, paying back a loan. So taking out an auto or consumer loan typically involves an ordinary annuity in terms of how you're going to pay off the loan. So the present value, what we think of as the present value of the loan, that's going to be the amount borrowed. So that's the original amount that you're financing. That does not include the interest. So the present value is what you finance. Once you accrue the interest, that's going to be the actual total amount for the account. So once you determine how much you're going to have to cover, how much is financed, the equal payments that you make, typically you're going to make annuity payments. They're equal payments made every month, something like that. They're going to cover both the principal, the present value, the amount you borrowed, and they're also going to cover the interest that your lender is charging you. So the way this actually works behind the scenes, the lender is going to calculate the total amount due up front. They calculate that at the very beginning. And then the cost to the consumer is amortized. It's divided up over the life of the loan. So when they calculate your actual payments that you're going to make to pay off your car, pay off your TV, whatever it is you financed, the payments are always going to be the same, but those individual payments are covering both principal and interest, and they're covering them in different ratios across the life of the loan. So in general, at the very beginning, you're paying off more interest than you are principal, whereas at the very end, you're paying off more principal and you're paying off less interest. So your payments are always the same, but how they're allocated towards these two different components you have to pay off, that's what potentially changes over time. And the way it's divided up, you can actually determine that based on the use of what we call an amortization schedule. So when you buy a house, for instance, your lender will create an amortization schedule which tells you how all your payments are structured and what sort of things you're paying off based on each individual payment. There are ways to calculate it. Calculating all the values from an amortization table or schedule is a little bit more complicated than we really need to get into. So we're just going to look on calculating the actual payment. What's the payment going to be month to month or period to period in order to pay off the particular loan we have to pay off? Okay, so let's look at a couple of examples. Suppose you buy a TV for $3,000 and you agree to pay for it in 18 equal monthly payments, and it's 1.5% interest per month, careful here, on the unpaid balance. What we want to know is how much are your payments going to be, and once you paid everything off, how much interest will you have paid? Now we've got to be really careful about the wording here. We're making 18 monthly payments, so we've been given the total number of payments, which also represents the total number of interest periods. Now we've also been given the rate per month. It's not 1.5% annual interest. That is the interest per period, the interest per month. So we don't need to do anything to adjust these numbers. This is going to be our value for I, and this is going to be our value for N. So as a decimal, 0.015, and then N is going to be 18. Now where we put our numbers in this problem depends on the numbers that we're given. The other number we have here is $3,000. Now $3,000 is the value for the TV. It's the amount you're loaned, it's the amount you're financing. That is the present value. The present value is always the principal. This is the original amount for the loan. So it's going to take the place of PV in our present value formula. Now again, how do we know if we're going to use PV versus using FV? You only use FV when the balance is increasing. Because we're talking about a loan here, we're making periodic payments, but we're making them so that we can decrease the value of the loan over time. By the time we've made all the payments, we want the balance to be 0. Future value applies when we're making payments in order to increase the value of the account over time. So present value, we're decreasing the value of the account. Future value, we're looking for the increased value, what it's going to be worth in the future. So we're going to use our present value formula. Here, payment is going to be our variable. The question is, how much are your payments? So PMT, that's the actual unknown, that's the variable. So present value, $3,000, that's the amount we're paying off. So not only are we going to pay off $3,000, but we're also going to pay off the interest that's charged based on our interest rate and the number of times they're going to charge us interest. So I'm going to plug in everything I know. There's our I's. Don't forget the negative. That's one of the easiest things to do when you're using the present value formula. You forget the negative on the exponent. That makes a major difference. So 1 minus 1 plus I to the negative n divided by I. Okay. Now, as with a lot of problems we've looked at, notice that this number, this is one fixed number multiplied by PMT, which is our variable. So a good place to start is to simplify all of that down in your calculator. So I'm going to go one operation at a time. 1 plus 0.015. Okay, that's everything in parentheses. Now that's raised to the negative 18th power. Now here's where we have to be careful. It's 1 minus that number, not this number, minus 1. We have to type the 1 minus first, and then we're going to pull in and copy that line with second and negative, which brings in that answer. So that's going to be our numerator. We're now dividing that by our value for I, 0.015, and that's going to give us our multiplier for payment. That's the number that's multiplied by payment. Payment is our unknown. So we want to divide out that number in order to isolate our unknown, and then we balance it by doing the same thing on the other side. So 3,000 divided by this number that we're then dividing out in order to isolate payment. So divide by second and negative for A&S, $191.42. That is going to be our periodic payment that we make, same payment every single time, in order to pay off this loan. Okay, well then our question is, how much interest are we paying? You're going to pay more than $3,000 when you pay off this TV because you're being charged interest. You have to kind of think about it, like, why do they charge you interest? How are they making money? Because if they give you a TV that's supposedly worth $3,000 and you give them $3,000, well, it's a one-to-one trade, right? So you're getting something that's worth $3,000, something physical, and they're getting cash that's worth $3,000. So they're not really making any money in a sense. Where are they making money in terms of the lender making money? They're making money by charging you interest. The actual interest represents a cost to you. It represents something where they end up with additional money and you don't have anything to show for it. So once you pay off $191.42 18 times, you're going to have paid more than $3,000, because not only are you going to have paid off this, the present value, the principal of the loan, but you're also going to have paid off whatever interest they charged you. So we're making this payment 18 times, $191.42, 18 times, for a total of $3,445.56. That's the total amount you're paying by the time you've made your 18 monthly payments. So from that, we subtract how much you actually were loaned, and the difference between the two, that's the interest that you were charged. So you were charged $445.56 worth of interest. Now, one situation where pretty much, well, I don't want to say everyone, but a lot of people will end up having to deal with at some point is paying off your house. So we will only look at the situation where you're actually making your mortgage payment. You have to keep in mind that when you make payments on a house, typically you're paying for a lot of different things when you make that monthly payment. Only some of it relates to the actual amount you've been lent. But you also potentially pay into escrow, which is going to be an account that you use to cover your taxes, cover your insurance, different things like that. So when you actually look at the monthly payment that's calculated by your loan agent, your loan officer, Some of that goes towards the house, and some of that goes towards the other things that you have to pay for as a homeowner. All that we're going to look at here is the component of the payment that represents the actual interest and principal that you're paying, not the additional things like taxes, like insurance, those kinds of things. So just the actual amount that pays off the loan. Okay, so for example, we put a $25,000 down payment on a new house, and we've determined that we have to pay $1,150 per month for 30 years. So that's going to be our monthly payment to pay off this house. If interest is 7.8%, and that's compounded monthly, what we want to know is what was the selling price of the house, excuse me, and then also how much interest are you going to pay over 30 years. So we flipped it around. Now we have the actual value for the payment. This is how much we're paying per period. We pay it 12 times a year for 30 years, so a total of 360 payments. And then our interest rate is 7.8%, and that's going to be compounded monthly. In other words, we're dividing that into 12 parts. Our question is, what was the selling price of the house? We could also call that the present value. It's the amount that we're paying off. So if we're talking about a loan, present value represents the amount that we were loaned. So the question is not quite just the present value, but what was the house sold for? Well, the selling price has two components. Some of it is financed. That's going to be the actual present value. That's the actual amount you were loaned. But the selling price of the house includes not only that, but it includes the $25,000 down payment. A down payment is just the money that we pay up front. So we pay that money up front. It doesn't actually accrue any interest because it's taken care of before the interest would kick in. So the selling price is going to be the present value for the loan, the actual amount that we financed, plus that down payment, that particular part of the house's value that we paid up front. So first thing we do need to find though is going to be that present value. So we need our rate per period. So 7.8% compounded monthly, so 0.078 per year divided into 12 parts. So let's see, what's that going to be? 0.078 divided into 12 parts. Okay, so 0.0065. Don't round, keep all of those decimal places. And then how many periods are there going to be? Well, your standard 30-year loan to pay off your house, that's going to be 30 years, and then once every month, so 12 times a year. So 12 times a year for 30 years, that's going to be a total of 360 payments and 360 chances to accrue interest. So first thing we need is the present value for the loan. If we're making this particular payment and we're making it 360 times based on how interest is accruing, what was the actual amount that we're paying off? How much were we actually loaned? In other words, what is the present value? So this is going to be the value for our payment, and then everything else is based on our value for I and then our value for N. Again, don't forget the negative. That's part of that exponent. That's going to be important. Okay, so in parentheses, 1 plus 0.0065. Okay, now that's being raised to the negative 360 power, raised to the negative 360. Okay, now it's 1 minus that amount. So 1 minus the amount we just found, and that is going to be our numerator. So we're dividing that by our rate per period, divided by 0.0065. And you'll notice we get a pretty big number overall, so 138.9. That's significantly larger than most of the numbers we've seen when we've evaluated that particular fraction. That's because we're talking about a loan that was originally for a lot of money. This is the amount we have to pay per month, and this is the total number that we multiply that amount by. So we multiply that by our payment of $1,150 per month, and that is going to be the present value. So $159,750.96. In this case, we weren't told specifically how to round, so we'll just assume cents, 2 decimal places. So what does this represent? This represents the amount we were originally loaned. That was the original amount of the loan. So the selling price of the house includes not only this amount, the amount that we were loaned, but it also includes the $25,000 that we put down up front in order to get the loan. So the present value plus the $25,000, that's the actual selling price of the house. So the portion that we financed plus the portion that we paid up front that we didn't actually need a loan for. So $159,750.96. Did I type that right? Yes. Plus 25,000, and there we go. That's going to be the selling price of the house. That is the list price. And again, keep in mind, there's a lot of things that go into buying a house, even up front, that wouldn't be included there. For instance, if you have to pay points, things like that, origination points, there are a bunch of different things that can factor in when you're talking about closing. Closing is when you actually put the money down, you sign everything, and they hand you the keys, you give them your down payment, all of that. There's a lot of different things that go into buying a house. All we're looking at here is the actual physical real estate we're buying, how much it counts for, how much we're financing, and then the payment that it's going to take to pay off not only the loan, but also the interest that we're being charged on that loan. Well, this is the amount that supposedly the house is worth, but by the time you pay off the house, you're going to have paid a lot more than that, or specifically, you're going to have paid a lot more than that. Keep in mind, this is not the amount financed because $25,000 was paid at the very beginning. This is the amount of the actual loan. This is the present value of that loan. This is what you're paying off with those $1,150 payments each month for the next 30 years. Well, how much are you actually paying in order to pay off this $160,000 loan? Let's see, this is where buying a house, the numbers start to look crazy. So $1,150, okay, per month. So that's going to be 12 times a year. And then that's going to be 30 times for 30 years. That's going to be a total of $414,000. So once you pay off the house, this will be the total amount you've paid in terms of actually covering the loan. So to cover a loan for about $160,000, you have to pay a total of $414,000. Well, there's a significant difference between those two numbers. This is the supposed value of the loan. This is the value of the house. This is the portion of that was loaned. But this is what you actually pay over the course of 30 years. What accounts for the difference? Well, the difference, that's your interest. So if you take the total amount that you paid minus what you're actually paying off, which is $159,750.96. Don't mix the two numbers up here. This includes the down payment, which is not charged interest. This is the only portion that's charged interest. So minus that portion that's charged interest, that is going to be the amount of interest you pay. So $254,249.04. Notice it's almost $100,000 more than the actual supposed value of the loan, which is close to the value of the actual house. That's just interest. We think of that as an actual cost to the consumer. I'm getting tongue-tied again. You have something to show for this money because you have the house that supposedly is worth this amount of money. This is money out of your pocket that you don't get to see again and you don't actually see any value for. So it's required in order to get the financing, in order to buy the house, in order to get the money lent to you in order to buy the house. This is the cost to you for that, but that's money that unfortunately is down the drain that you don't get to see again. This is the only money that you then have something physical to show for. So if you've ever wondered why anyone would lend someone $160,000 and lend it for such a long period of time, you think about it, your loan officer, the person who writes the original loan, more than likely they may not even be alive by the time you pay it off 30 years from now. So why would they be willing to loan you so much money? Well, they loan you so much money because look how much money they're going to make. This is money they're making. This is money that then replaces the house. This is money that the actual lender is making off of your loan. So not only is there a chance to make a lot of money off of the loan, but the loan is relatively low risk in the sense that what happens if you choose not to pay? Well, they come and they repossess your house, they foreclose. So overall, it's pretty low risk for the lender just because they are in it to make so much money. And if for some reason you choose not to pay, well, they just get the real estate back, which means they recoup all of that money that they then lent to you. So there's a lot that goes into buying a house. This is just a sense of some of the basic calculations. And then keep in mind, again, the $1,150, that will be the same payment every single month for the next 30 years, as long as you have a fixed loan, as long as the interest rate is fixed. But the way that's spread out from month to month changes. So the earlier payments you make, you'll be paying more in terms of interest. The later payments you make, you'll be paying more in terms of principal. So how do you pay it off faster and how do you save money? Well, ideally what you'll want to do, besides making that required $1,150 payment, you can specifically add an additional amount and say you want to direct it towards principal exclusively. So if you just pay an additional amount, in theory, they may just charge it towards the balance of the loan. Whereas if you pay it towards principal directly, that particular amount of principal can no longer accrue interest. So not only have you paid down that principal, but that particular amount also represents a bunch of interest. Over 30 years, that amount you just paid off would have accrued interest. If you pay it off then it no longer has time to accrue interest. So even just paying something like $100 extra, that $100 is worth more than $100 30 years from now. It's worth the original amount, but it's also worth all of that additional interest that it would have accrued. So that ends up saving you more than $100 in the long run. It also saves you the amount of interest that you would have been charged for that original amount. So just to sum up, biggest thing, difference between the principal, the present value, and then the future value. Future value is what the account is worth in the future. Present value is what the account is worth now, which we also call principal. So if you're looking at a future value problem, you can identify it by the situation increasing in value. So you're making these periodic annuity payments, same amount, equal periods, but you're making it with the goal of increasing the value, the balance in the account. If we're talking about a present value problem, present value is what the account starts with, but the idea is in general, we're decreasing the value of the account. So as we make payments, we're not increasing the value, we're not increasing the balance in the account, we're actually making those payments to take that present value and to decrease it over time and pay it off.